So far, we have learned that you can use Amazon Elastic Container Service to build your microservice application by using containers. And those containers can be deployed in Amazon Elastic Container Service, which is an orchestration service where you can manage your application code, data source integration, security configuration, update, network configuration, firewall, and management tasks. We also learned that Amazon Fargate can be used as a launch type to host your cluster on a serverless infrastructure that Amazon Elastic Container Service manages. But what does serverless mean? Serverless is the native architecture of the cloud that enables you to shift more operational responsibilities to AWS, which can increase your agility and innovation. Serverless enables you to build and run applications and services without thinking about server. Your application still runs on servers. However, AWS does all the server management tasks such as a server or a cluster provisioning, patching, operating system maintenance, and capacity provisioning. So how we can define serverless as an operational model that can be including the following: no infrastructure to provision or to manage, no servers to provision, operate, or patch. Automatically scales by unit of consumption, scales by unit of working or consumption rather than by server unit. Pay for value pricing model, you pay only for the duration that a resource runs rather than by server unit. Built-in availability and fault tolerance, no need to architect for availability because it is built into the service. So the benefits of serverless: lower total cost of ownership, focus in your application, not in your configuration, and you build a microservice application. AWS has many offerings that you can use to build a serverless architecture on AWS. So far in this course, you have already learned about several of them, including AWS Lambda, and we will study AWS API Gateway and AWS Step Function, as well to build a complete serverless architecture. So let us look to AWS Lambda. AWS Lambda is a fully managed compute service that runs your code in response to events and automatically manages the underlying compute resources for you. Lambda runs your code on a high availability compute infrastructure and performs all administration of the compute resources, including server and operating system maintenance, capacity provisioning, automatic scaling, code monitoring, and logging. AWS Lambda natively supports Java, Go, PowerShell, Node.js, C#, Python, and Ruby code, and provides a runtime API that enables you to use any additional programming languages to author your function. There is Lambda at Edge, which is a feature of Amazon Cloud Front that enables you to run code closer to user of your application. And remember this for the exam, which improves performance and reduces latency. Lambda Edge runs your code in response to events that are generated by the Amazon Cloud Front Content Delivery Network. Lambda Edge enables you to run Node.js Python Lambda function to customize content that Amazon Cloud Front delivers. So how AWS Lambda works? AWS Lambda integrates with other AWS services to invoke Lambda function. A Lambda function is a custom code that you write in one of the languages that Lambda supports. You can configure a trigger to invoke a function in response to resources lifecycle events, responding to incoming HTTP requests, consuming events from a queue, or run on a schedule. An event source is the entity that publishes the event to Lambda. Your Lambda function processes the event Lambda function in your behalf. Lambda functions are stateless, which means that they have no affinity to the underlying infrastructure. Lambda can rapidly launch as many copies of the function as needed to scale to the rate of incoming events. When you create Lambda function, you define the permissions for the function and specify which events trigger the function. You also create a deployment package that includes your application code and any dependencies and libraries that are needed to run your application code. Finally, you configure runtime parameters such as memory, timeout, and concurrency. When your function is invoked, Lambda will run an environment based on the runtime and configuration option that you selected. When a Lambda function is invoked, the code begins running at the handler. The handler is a specific code method or a function that you create and include in your package. You specify the handler when you create a Lambda function. Each supported language has its own requirements for how a function handler can be defined and referenced within the package. After the handler is successfully invoked inside your Lambda function, the runtime environment belongs to the code you wrote. The handler always takes two objects, the event object and the context object. And it's very important for you guys to understand. The event object provides you information about the event that is triggered by the Lambda function. This event might be a predefined object that an AWS service generates or a custom user-defined object in the form of serialized string. An example of such a string might be a plain old Java object notation or a JSON string. The content of the event object include all data and metadata that your Lambda function needs to drive its logic. The contents and the structure of the event object vary depending on which event source created it. For example, an event that is created by API Gateway contains details that are related to the HTTPS request that was made by the API client, such as the path, the query string, and request body. However, an event that is created by Amazon includes details about the bucket and the new object in Amazon S3. Now, what about the context? The context object is generated by AWS and provides metadata about the running time environment of that object. The context object enables your function code to interact with the Lambda runtime environment. The contents and the structure of the context object vary based on the language runtime that your Lambda function uses. However, at minimum, the context object contains the AWS request ID, which is the property is used to track a specific invocation of a Lambda function, the log stream name, the CloudWatch log stream that your log statements will be sent to, and the get remaining time in milliseconds, which is the method return the number of milliseconds that remain before the running of your function times out. So in Lambda function, the configuration and billing, you will look to the memory. You specify the amount of memory you want to allocate to your Lambda function, and the Lambda then allocates CPU power that is proportional to the memory. Lambda is priced so that the cost per 100 milliseconds of function duration increases as the memory configuration increases. The timeout, you can control the maximum duration of your function by using the timeout configuration. You can set that timeout value for a specific function to any value up to 15 minutes. When that specified period of time is timed out, AWS Lambda stops the running of your Lambda function. This can prevent higher costs that come from long running functions or infinite loop. You must find the right balance between not letting the function run too long and being able to finish under normal circumstances. So the best practices for Lambda function is to test the performance of your Lambda function to make sure that you choose the optimum memory size configuration. Load test your Lambda function to analyze how long your function runs and determine the best timeout value. And let us now look to a demonstration of creating an AWS Lambda function. You can create Lambda function to perform various tasks. This example uses a browser-based game that simulates a slot machine. The game invokes a Lambda function that generates the random result of each slot poll. The function returns those results are the file as the file name of images that are used to display the result. The images are stored in Amazon S3 bucket that is configured to function as a static web host for HTML, CSS, and other assets that are needed to present the application experience. So in this example, we show how Lambda can be used in the solution for order processing. A custom upload of a transactions file to an S3 bucket, which triggers the running of a Lambda function. A Lambda function processes the transaction file and update the customer and transactions DynamoDB table. Changes to those transaction DynamoDB table trigger a second Lambda function to aggregate the transactions and update the total in the transaction total DynamoDB table. It also pushes a message to the high balance alert SNS topic. That SNS topic sends an email notification to the customer and updates the credit collection and customer notify SQS queue for payment and processing. So the Lambda layers enable function to share code easily. You can upload a layer one time and reference it in any function. Promote separation of responsibility. Developer can iterate faster on writing business logic and enable you to keep your deployment packages very small. It has some limits up to 5 layers of storage and 250 megabyte per layer. And let us look to a demonstration about using AWS Lambda with Amazon S3.